is equal to m2g. It's now a math problem. Typically, we have mu sub k here. Masses I didn't give. So let's make mass 1 5 kilograms and mass 2 equal to 3 kilograms. Why not? And let's put this on a mysterious planet, a strange planet where g is equal to 10 meters per second squared. I thought so. So the first thing I'm going to do is I'm going to substitute this in for y2. So I have m1g minus tension is equal to m1a, and then tension minus uk m2g, and that's a subscript k, equals m2a. Now the point at which you plug the numbers in, that's up to you. The general recommendation is don't plug numbers in until the very end. Now, in a problem like this, it's not going to make a difference one way or the other. There are problems where it's really convenient not to plug numbers in until the end, because if there's a multi-step problem, it could be just a matter of, okay, I got my end, I come out with some formula here with all letters, I plug the numbers in, and then the next part, I have to make some small adjustment. Okay, not a problem. Let me just make the small adjustment to the formula, as opposed to having to start from scratch again. Ultimately, in these problems, you're generally solving for acceleration. I did not state that explicitly, but that is a typical thing, so I'm trying to figure out what is the acceleration. Because it's an ideal rope, these tensions are the same, and so if I just add these two equations together, tension's going away. So what I'm left with is m1g minus tension plus tension minus uk m2g is equal to m1a plus m2a. I just added the left sides, added the right sides. Oh, that last S is solved, that's what we're doing now. So we end up with m1g minus mu k, m2g equals m1 plus m2 times a, factoring a out. And so a equals m1g minus mu k m2g divided by m1 plus m2. Yep. Divided by m1 plus m2. And now we plug each other. What do we get? 5. So 50 minus 3 times 10 times 24 minus 12 divided by 8. So 4.71. Yep. Units?
Meters per second squared?
Yes. Or should I include the question mark?
Yeah, just include it just in case. I don't want
It's,
anybody to
it's
think.
acceleration, that's meters per second.
Yeah. I don't even want to think that I know what I'm doing.
Oh, you did. You did know what you were doing. Because we're starting with SI units. We're starting with kilograms. We're starting with meters per second squared there. This is unitless, so we better be getting typical units of acceleration there. Couple things to point out. Number one, my acceleration is less than acceleration due to gravity. I hoped it would be that way because there's no way that this whole system is going to be as if this thing's in free fall. So we got something less than. We got a positive value. I would expect a positive value because we said the acceleration was in the positive direction, so I better get a positive number. If we made no mistakes at all and we got a negative acceleration, that would mean that, oh, it's going the other way from what we assumed. Anyway, that's a full setup of the problem. I forget what made me want to go do an entire one right now, but
I think it was something that I asked, and I apologize for that.
Yeah, Anna asked something and you're like, why don't we do a problem?
Yeah, what was your question?
I don't know.
I'm sure it was answered.
I'm sure it was answered.
Yeah.
Thank you.
Yeah, no, I'm trying to remember. Well,
We had the
I'll look at
video.
the videotape later and then I'll go, oh, that's what she was asking. Man, could have done that in 2 seconds. Anyway, any questions about all of this?
Is this how we're gonna find formulas for what we need to find in the equation, or are we, in the problem, or are we not gonna do that? We're just gonna have units and know how to put them together?
I'm not 100% sure what you meant by that question. The process that we just went through here, where you start with a force diagram and then you
Yeah.
come up with equations of motion, yeah, we'll be doing that quite a bit.
What I meant by my question was, when we usually start with like cake formulas, we had a way to find them, like how we broke it down into, this is how we got this from this. Is this what we're doing here? Like acceleration will always equal whatever this mass minus the UK, you know, over what?
I would really not want to say always. The process, the steps that we went through are gonna be the same again and again.
Okay.
This might be the last time you ever see that formula.
Okay.
This is not, if you're into the, give me the situation, what's the formula, yeah, it's not working. That's not gonna happen.
Thank goodness that's not me at all.
If you want the, except for the fact that F equals ma, this is the same throughout. The total force is equal to the mass times the acceleration of the object. We try to get it to the point where it's a physics problem, where it's a math problem. So physics gets us to here, math takes us to here, and then physics snaps back in with going, does this make any sense?
Mhm.
So I think what he was asking is, can we do just the physics part and get rid of the math part? But it sounds like we have to do the math part every time and show exactly this process.
There are 3 types of problems that I typically put in test 1B.
Yeah.
I mean, there's 3 that I expect that are gonna be on there. One's complex force diagram. So concentrating on the erased facades, but the F. Another one is, I give you the force diagram and ask you to come up with the equations of motion. So that's as far as you go on that one.
Okay.
There's another one that I've been doing more recently where I give you this and ask you to create the initial problem. I kind of like those.
Yeah, so, I'm kinda, so, I see how, like, you were able to find acceleration towards the end with that equation, but I'm confused, like, why did you do, what you did on that right side to get?
Why did I just add them together?
Yeah, pretty much.
I needed to get rid of tension, because I really don't care what the value of tension is. And so one way of doing it is, if I add the left-hand sides, I got a negative tension and a positive tension, and they would cancel out. Some students prefer instead to solve for tension in one of the equations and then substitute it into the other. That's fine too. But I do have 2 equations and 2 unknowns. I don't know tension and I don't know acceleration, so I have to somehow combine the 2.
So then, why did you need, like, what you did, on top of that to get there?
Wait, sorry, on top.
Yeah, so those first 3.
These first 3, these are the ones that are coming directly from this. In the process, we come up with the equations of motion, then I substitute in the formulas that I know, and there's the 2 formulas that are written here in green. I did that substitution, and then it comes to the math part of solving. So that from here, I have 3 equations, 3 unknowns. I got rid of one of them by substitution. Y2 is equal to M2G, I'll plug that in. And then I now have 2 equations, 2 unknowns. Since I'm solving for acceleration, I got rid of tension. And now I have just acceleration to solve for it.
Okay.
Are you gonna include the formulas on green, especially the like Fk is equal to mu, Ky? Are you?
Oh, yeah,
gonna-
that would be included, on
On the test.
And then there's another one for static, just for the fun of it. It's an inequality. And when we get more formally to the friction section, I'll explain why it's not an equal sign there.
Where you went over here with the long equation, yeah, right there. How did you get where you have M1 plus M2?
Okay, this part,
How did you do that based on?
because I had, on the right-hand side, I had M1A plus M2A,
Right.
and then factored. I have a common factor here, and I pulled that out, and I'm left with M1 plus M2
Okay.
times an A. And if you distribute, go in the other direction, you.
Oh, okay, I see, that makes sense. Okay.
And I guess potentially for some of you, you're looking at this and go, oh, that's why we did that. If you ever wondered in math, why do we need to learn this? Here's some of those times.
I was glad we touched on, the unit circle, because that, you know, I thought to myself, well, we'll never use this, and then now we do.
I always thought the F equals MA equation was deceivingly simple, you know what I mean?
I had one professor in graduate school say, it's called conservation of complexity. The simpler the equation looks, the more complex each letter is. Any other questions on this before we do? Box on ramp, pulling other box on ramp. Alright. And even though your minds might be working this way, we're doing friction last. Just leave it.
So what's this called? Box on ramp pulling other box on ramp?
Yeah, so box on ramp. Pulling, I guess it's box on other ramp.
Are there two separate ramps? Oh, okay.
Change that. And the rope on the left side is not parallel to that side of the ramp. I deliberately have this, there's an angle between the ramp and that rope. A non-zero ramp with appearance. And just to simplify it a little bit, we'll go ahead and make the ramp part of the ground.
Would that make the rope not ideal because it's not parallel with the ramp?
No, it's still ideal. Let's go ahead and make that explicit idea. We've done box on ramp already, so this is just double that. And therefore, it's just as simple.
Obviously.
All right, friction last. All right, so what do we start with?
Gravity.
Yeah, and it's your turn. What is wrong with what he said?
Is gravity, did my acceleration do to?
Force due to gravity?
There we go, force field, right.
Okay.
Otherwise, in this case, known as,
Acceleration due to gravity?
Weight, it's W with the little
Yeah, weight.
thing, weight.
Got it.
all right, so weight, which way does weight act?
Down towards the largest amount.
Yes. W1, W2, W1, W2. And again, one of the other things, I drew my weight one so that they're directly opposite each other. Even though mass one is on the ramp itself, I didn't draw weight one going up on the ramp itself. It's, again, weight is with the earth. Doesn't really matter where I put it, just as long as it's on the earth somewhere. Or planet or whatever that we're sitting on. Wherever these experiments are conducted.
Definitely not Jupiter.
True. I guess for Uranus and Neptune as well.
Yeah, giant gas giants.
All right, so that's done. What next?
Normal.
Normal force?
All right, normal force acting which way on one?
It's going up on the box and down.
Okay, the finger gesture was right, the wording, just be careful about that.
Up and
Up to the left.
Right, cause it's.
And then similar here. That's normal, okay. They have only two small objects other than the Earth, so I guess unless the two objects are touching each other, that's all we can do. All right, what next?
we don't have another.
Okay, that's simple.
Oh, we didn't draw the rope.
I was gonna ask about that.
Thank you. Oh, yeah, therefore, there's another normal. Thank you, sorry about that. And now, I guess tension, since we're doing friction lines.
Yep.
Which way is tension acting on what?
On box two, it's pulling up and to the left, and then it's got the complementary force on the rope, pushing, or pulling towards box two.
Same thing, just opposite direction.
I'll go with the spirit of what you were saying. Tension done. Now, which way is friction going to act?
Do we need more information?
What information do you need?
We need to know what the relative movement is. So we need to know which boxes.
Don't we know that
active.
there's friction regardless, cause
Yep.
there's contact, like right there?
We know there's friction, yeah, but which, well, actually, we
Direction.
don't know that there's friction. Actually,
We
yeah,
need to know if
it's-
it's sided towards one or the other.
Yeah.
Yeah.
You
Now-
know the masses of the boxes.
We need to know masses and the angles. Because as you did in the lab, that the mass and angle both had an influence. So I did not give you that information on purpose, because which way friction is acting really does depend upon other information. If we knew the masses and the two angles, we could calculate it. Now, if I gave you the masses and the angles and asked you, and then you start doing the force diagram, without doing the calculations, you still don't know which way it is. So typically in a problem like this, I know that there was a test problem I did like this a couple years ago, where the first question was, they're in equilibrium to start with. What is, I think I gave one angle and two masses, and you had to find the other angle so that it stayed in equilibrium. And what would equilibrium mean in this case?
No,
Nothing's moving.
no relative movement?
Not moving is not necessarily true.
It's static.
That would be static equilibrium if they were not moving at all.
No acceleration.
That's the key, or the total force is zero. So if you add up these three forces, it would add up to zero. Those three up, it would add up to zero. You set up a coordinate system. In that case right there, you don't know which way is, well, it's not going to accelerate, so acceleration is zero. You just pick a direction as positive. So if you pick that positive, I'd recommend picking that positive so that they're basically going together. I then increase the angle on one side, at which point it then becomes clear which way it would go. Now, if it's not in equilibrium, I gave you the masses and the angles, and you had to figure out which way it's going to move. Again, you just pick a direction to start with. You calculate acceleration. If you get acceleration being positive, that means, oh, yes, that's the way it's going to go. Acceleration negative, oh, that means it went the other way. So typically you'd solve it first without any friction at all, and then once you know the direction of friction, you bring that into it. We will go through just an absolutely thrilling example of this later. But for this one right here, let's assume, oh, there's a mistake. What's the mistake before we bring in friction? There's a problem with tension.
Is there tension on the pulley?
No, it's an ideal rope.
Okay.
We didn't
Does that-
label the tensions themselves.
Not an issue with that, it's an ideal roof.
does it have to deal with the fact that there's two, like, I don't know
There's,
where I'm going with this.
there's gravity on the pulley, isn't there?
I mean, weight of a pulley's part of the ground.
Okay, so then the only other thing could be normal force.
Sorry, I'm so sorry.
No, go ahead.
I think
I'm-
it's the direction of the force tension on the left side because of the angle of the road.
Gee.
I even did that on purpose so that this wouldn't be like that.
Wow.
That tension's sort of going off like that. And that one sort of gone more like that.
Oh, that's interesting.
See, I obviously knew that was happening, I just didn't think about it in the moment. I just looked at it and I was like, well, obviously he meant that was gonna be in the middle, so, his drawings are perfect.
Yeah, no, that was a deliberate draw like that. Alright, so now, assume it's gonna go in that direction. V for speed. In which case, which way is friction acting on mass two?
That one.
And which way on mass one?
The opposite direction.
I assume
Same direction.
similar to before, as in down the ramp? When you say opposite direction, in vectors, opposite direction means
Yeah.
it would be that way. So
Oh.
mass one's moving up the ramp, the friction's gonna be acting down the ramp on it, and then up the ramp upwards on the ramp.
So, the reason that was is because there's more,
I arbitrarily chose, let's assume it's going that way.
Wait, if
oh, okay.
the box is moving that way, then why is the friction going with it? Shouldn't it be the
Because,
The friction's opposed to the motion.
Right, but, oh, yeah, never mind, okay.
You look at it that way?
Yeah,
Okay. It's not the friction you want.